So next we discuss Stokes Theorem, which we have already done in the last course a little bit. So we quickly review this. Given a surface S and it's bounded, the surface S is defined by its boundary curve C and a vector function V, what Stokes theorem tells us is that if you take the curl of at each point, curl of the vector function, and then calculate its dot product, that is the flux of the curl through dA over the whole surface S, then this is nothing but that is equal to the function evaluated along the curve which is bounding the surface V dot dl for the whole curve. This is the curve C, but this is a closed curve because that defines the surface. To be able to understand this a little better, okay, let us I think I'll just give a physical and geometrical meaning. Let's say is a flat curve, and let me make small differentials. I'm showing it big ones, but these you can count as small pieces, okay, differential area pieces, okay, in xy plane, let's say, to be specific. And then I want to find out what is the circulation around this point in any of that circulation. So that is nothing but del cross V I have to calculate. And each simple area, what is dA? That in this small area, that is delta x in this particular instance, delta x, del y, and the normal is in k direction. So we know how to calculate del x and del y. Let's make it a magnification, okay, of del x. Okay, so let's say this is del y on this side and this is del x on this side. Okay, and this is the center point around which we want to calculate del cross V. So let's say this is the path 1, path 2, path 3, and path 4. Okay, so if I consider that there is let's say a x or Vx in this direction, and then Vx can be here, it will be slightly larger. And how I can write down? That is, in here is Vx plus, how does Vx change with as I go over in the y direction and into delta y. That is what I have, okay. So that is, whereas this is only Vx. And similarly, I can consider that suppose this is Ay, this is, Vy, and this is Vy. So this will be Vy plus how del Vy changes with del x, okay, into del x. So that will be this. So how do I calculate the circulation totally? Like what I do is this boundary and then go over and calculate the line interface around it. And that gives me the circulation dot dA. Okay. So what will be between, let's say, 1 and 3? So quite clearly, by taking the circulation around this path, what we have obtained is that what is turning right and what is opposing it, we can write it down the extra amount as delta Vy by delta x into delta x, that is the extra amount, and over delta y. This will be opposed by delta Vx by delta x. This is delta y, over delta y, and this is delta x.
Okay, so that is the circulation. If I go around this small element delta x and delta y, then that is the circulation. Now, as I had argued earlier, so you can this is nothing but delta Vy by delta x minus delta Vx by delta y and delta x into delta y, which I can now replace by saying that this is nothing but dA if delta x and dy goes. So what I have is delta Vy minus del x minus delta Vx by del y dA. Now this clearly reminds us that this is nothing but the I can say that this is the z component of del cross v for this particular case. Okay, the z component, and that is because z component is dA is in the z. Okay, so I can always write down this as the k component with the dot product with the dA. But what we have done, we have obtained it by taking a circulation, which means for the small ith loop, what I have actually done is calculated v dot dl over that small ith curve. Now, if I do this for each of the elements here, okay, then I can say that I'll sum it up. Let's say for all the ith loops, okay, I sum up the ith loop circulation, okay, and so that would, if I take the dA to be small, okay, so that would be also, let's say, sum of del cross v of each of these dot dA over each of the I. Now if I take the limit, then this would be, since it is sum of all i's, obviously it is sum of the whole curve, and hence this will, I can write down as this itself as integral of v dl. Now it is integrated over the paths, the curve C, which is the full, because we are summing it over all the small elements, and that is nothing but over the surface del cross v, that is the curve, dot dA. Now I have shown it for a flat surface, and I've shown it for a particular case and generalized it, but this is true for all kinds of surfaces. I will not prove that, but geometrically one can understand that what is happening is that if I take one small area L, and now I take circulation, while I'm taking circulation, I'm taking this path. Now if I take the neighboring one, then I would have gone like this, this, and this. If I've taken this one, then I would have gone like this, this, and like this, right? And if the top one, then I would have been going like this, and the side one will be again going like that. So while I'm summing up, all the internal, gets cancelled out for each of the arms, and hence what remains, if I sum up all of them, is only the border one, okay, which remains uncompensated, and hence what I get is the circulation around the path, and all the other circulations, each arm gets cancelled. Simple idea, but this can be generalized to any surface and not just any flat surface that I have shown. So that is the essential content that everything gets cancelled out inside, and what you get is the paths only of the curve C outside this. So what we obtain is that if I know at each little piece, okay, if I know del cross V, and I know in which direction is this area, then I can find out in some sense the flux of the curl throughout, okay, everywhere. And that is same as if I take the line integral around the border as a fundamental theorem. So, and there are corollaries which I'll now discuss. So, as a theorem, this is extremely powerful. And remember, this is a purely mathematical theorem. Okay, we are not talking about any physics at the moment. Okay, so it's a purely mathematical result. It has important consequences.
But there are important consequences. Okay, so the important consequences, I have shown it for a flat, but this could be any three-dimensional surface. So a corollary, okay, which is an important corollary of one is, suppose suppose this is the curve C. Okay, and so I can calculate V dot dl. Now this V dot dl will be the same for any surface that it bounds. Okay, for example, that could be another surface which is bound like that. Okay, so in corollary one is that the del cross V dot dA over the surface S, okay, is independent of the surface chosen, is independent of the surface chosen for the same bounding curve C. For the same bounding curve C. Okay, so this is the curve independent. Then there is another important corollary which is easy to see. Okay, it is easy to see, but it is important is very useful. That is, what would be the suppose there is a closed surface. Obviously, for the closed surface, for example, in this case, I can have let's say one curve here, and suppose this was a closed surface. Okay, then while calculating this surface, I'll go like that. And for calculating this surface, I'll go in the opposite direction. So this will be 0. So this quantity, okay, over the closed surfaces is always 0. This actually comes from the same corollary as this is a corollary. Extremely important result. Suppose we have a surface in which there is a hole, let's say. Okay, then I'll go, of course, while going, I counterclockwise, and the region over which I'm doing it is on my left. Okay, so while considering this path, so there are the two bounding paths. So this path, I should go in such a thing that also is on my left. So I will go on this inside curve such that the region which I'm doing is on my left. All right. So this is if there is a hole. So these are some important. We'll of course consider very simple surfaces, but the generality of the results is what is important. Let's take up an example. That's the best way, and that is what is important in this course. Okay. So let's take an example of the proof of this theorem, not proof of this theorem, example of instantiation of this. Okay, let me call it 1.C3. This is about Stokes theorem. is about Stokes theorem and in Cartesian coordinates. I'll take the example in Cartesian coordinates, if in Cartesian. So what is given is a vector function which is like y k, and the surface that is and this is, let's say, x, y, and z. Then the surface is a, and let's say 2a. So this is this triangle. So that this is a, this is 2a, and this is a on the axis. Okay, so which means we have to prove Stokes theorem by saying that what is del cross f across this surface, across this whole surface, okay, and then show that v dot dl while going by this, and this, okay, is the same. The left hand side and right hand side are the same. Let us state it again. Okay, the del cross v dot dA over the surface S, this is the left hand side, and the right hand side would be the curve C, okay, v dot dl. Okay, so let us first evaluate the left hand side. For left hand side, first of course you have to do del cross v, del cross the vector function, and that's easy in this case because this is I, j, k, and del by del x, dou by dou x, dou by dou y, dou by dou z, and in this case what is given is 0, 0, and this is y. This is very, very simple because all the components are 0 except the ith component in which survives 1. So this is really only the unit vector I. So for this particular function, given function, okay, the del cross v is I. So what will be the integral? Integral on the left hand side is integral of del cross v dot dA. Okay, that's so dA is pointing, of course, it's a flat, so it is pointing in the normal to the plane, and but del cross v is only in I direction. So this is like I dot dA integrated over. So this is nothing, but we can calculate it, or you can even directly write it down. Okay, by saying that this will be the projection of this this flat area onto the xy plane. Okay, so dot I. So this is the xy plane. In the xy plane, the area is, so that's just that projection of that, and in xy plane, the projection area is half. This is A base into 2A, so this is equal to A. So that's easy to calculate in this particular case. You can do a much better calculation also. So you could actually, if you want to do it not by arguing, but in some general way, then if this is A, then calculate the vector AB, and then C, and then the area by vector area would be given by half AB cross BC. It's easy to do that. Okay, this will also, you see, that will be A square, and there will be a vector which will be in the direction of M. You could also alternatively do this, but in this case it is simple to get that this integral on the LHS is A square. Now let's go to the RHS, that is V dot dl, and there are three paths. Let me call it path 1, path 2, and path 3. So, and we'll do this separately. So for path 1, is this for path 1, you can see that, so we have to calculate v dot dl for each of them. Okay, so for path 1 is, you can see that how do I write down my dl? My dl is only in the xy plane, only in the xy plane, and hence it is dx I plus dy j, but my v is y in k. So this is perpendicular to that. So v dot dl is equal to 0. So everywhere, so I don't have to even integrate. Okay. So for this path, integration is not required, because the v is pointing in k direction, but the dl is in the xy plane. So that's equal to 0. Now let's go to the next path 2. Path 2. So there dl is in the, as you can see, dl is in the yz plane. Okay. So this is dyj plus dzk, but with a condition. Okay, this line. So this line is BC line, is z is equal to minus y by 2 plus a. Check that is what it z is. If if y is 0, then z is equal to a, and if z is equal to 0, then y is equal to 2a. That's correct. Okay, so that is, and in that case dz is minus dy by 2. So v dot dl would be y k dot. Okay, so this is my dl, but I can replace on the dz by minus dy by 2, and this will go to 0. So the only thing that will survive is minus dy by 2k. So this is minus y dy by 2. Okay, so then integral v dot dl over path 2 is equal to minus y dy by 2, and then, but you have to make sure, that is important, that we are going from y is equal to z is equal to z, or y is from this direction. So in this direction, which means y has to go from 2a to 0. Okay, this limit is important, otherwise you'll sign get wrong. So this y has to go, because 2 to 0. Okay, so that would become, so half, and y square, so minus y square by 2, or let's say minus half y square by 2. This is 2a to 0, and so this will become also a square. Okay, this is path 1. Path 2, we still have one more path to go. This is path 3. Path 3, you can see already that y is 0 everywhere, right? Because it's in a zx plane. And if z is 0, v is equal to 0. So hence I need not calculate. So path 3, is v is yk, and since y is equal to 0 all along the path, v dot dl is 0 for path 3. So the total, okay, so total is 0 plus a square plus 0 for the whole. Okay, this is for the total, this is for the whole, all over the whole path, v dot dl. This is equal to a square. And indeed, our answer is a square through line integration along the path. And we had already calculated the left-hand side is a square. So this is proven. All right. You can try and do for the same thing. I can suggest that you can also try, let us say, another surface, and that this time in cylindrical coordinates, and then prove that. Suppose I can suggest that let's you try this at home. We have a something like this, a cylinder. Okay, let me draw this slightly better. Okay, our radius r, and in this direction. Okay, you can prove the same cylinder of radius. So this is the surface is actually this, and the curve. So and the bounding curve is this. So this is like a cup or a glass. Okay, so a metallic glass, open surface. Okay, this is closed. This bottom is closed on this surface. So that is the bounding curve is this circle. Let's say at A, and radius is r. Prove the left-hand side, right-hand side. Okay, this will be in cylindrical system. I'm just suggesting that as a possible extension of this in cylindrical system, because I have not done in the cylindrical system. Okay. Okay, so we have done the three theorems, and I have now it's important. So let me now summarize by saying that what is called the Helmholtz theorem. It's called Helmholtz theorem. In this, actually, whole of electromagnetics, mathematically speaking, can be reduced down to this theorem. That is, if you are given divergence of, let's say, force field, or F is a vector function, and del cross F, okay, then the theorem we will not prove, we'll just state it, that F can be uniquely determined if boundary conditions are given with some condition on F, that F should goes to 0, okay, as R tends to infinity. If it is F is well behaved in that sense, that if F goes to 0 as R tends to infinity, and if its divergence is known and its curl is known, okay, then F can be uniquely be determined. Okay, that's the Helmholtz theorem. So, in fact, okay, we already have seen that if del cross F is 0, that is, if it has no curl, okay, if it is a curlless rotational, then F can always be described as a minus grad of V. All right. So, in fact, one can summarize all the results, associated results. It's irrotational or curlless fields. Then the following statements are all equivalent. I have said this, it is put together as a theorem. The following are all equivalent. They imply and are implied by. If del cross is equal to 0 everywhere, that's important, then F dot dl from A to B is independent of path. We have already seen that. Okay. And for a closed path, of course, 0. And F can be expressed as minus grad of V. Okay. But potential is not unique, because you can add any constant can be added to it, but it can always be expressed as a potential. These are already familiar for conservative forces. Electric field is a conservative force, gravitational force is a conservative force, and so these all four statements are equivalent to each other. Del cross F is equal to 0, F dot dl is independent of path, and for a closed path, F dot dl, like work done, is 0, and F can be expressed as a negative of a gradient. All right. So similarly, we can, for if divergence is 0, if divergence of a field is 0, and then F can be expressed as a curl of A. Why is that? Because curl of divergence of a curl is always 0. So I can always express F as a curl of another vector function, okay, that is A if divergence is 0, and which are called as solenoidal or divergence-less fields. That is, if, let's put down all these equivalent statements. If divergence of F is 0 everywhere, then F dot dA is independent of the surface. That we have just seen. Okay, and F dot dA over a closed surface is 0. And F can be expressed as del cross A. That is, the A exists, but it's not unique. You can add the grad of any scalar function to it and still be true. F is del cross A. All right. So, in fact, all of electromagnetism that we are going to do falls into this class. This course is all about two such fields. Okay, electric field, which can be expressed as minus grad of V, and a magnetic field, which can be expressed as a curl of A. This is irrotational. Del cross E is always 0, and here divergence of B is always 0. So you can see the importance of, in mathematically speaking, these two theorems are related to, one to electric field E and one to magnetic field B, and that's all we do in this course.